When you think about black holes, you probably pictured these cosmic monsters, right? These regions of space-time so incredibly dense that nothing, not even light, can get out. But what if these cosmic titans are also the key to solving an even bigger mystery? What if they're the ghosts in the universe that we've been hunting for all along? And that question right there, that's what's getting cosmologists so excited right now. We're going to dive into how some of the most familiar objects in astrophysics could actually be the solution to the universe's greatest unknown, dark matter. But okay, first things first. Before we go chasing cosmic ghosts, we need to ground ourselves in what we actually know. We need to get familiar with the monsters we can actually see. I mean, it is just incredible how fast we went from pure theory to actually seeing these things. For 50 years, black holes were just this mind-bending idea that fell out of Einstein's equations. Then John Wheeler comes along and gives them that terrifyingly perfect name. But it's really just in the last decade that they've snapped into focus. First, we heard them collide thanks to LIGO. And then we actually saw the shadow of one. Suddenly they were very, very real. So here's the key thing to remember. The black holes that we've taken pictures of, the ones we've heard crashing into each other, we call those astrophysical black holes. They're basically stellar corpses. A giant star runs out of fuel, its core collapses under its own massive gravity, and boom, you get a black hole. That's the standard story. But it's not the only possible story. All right, let's switch gears and talk about what is arguably the biggest puzzle in all of cosmology. See, when astronomers look at galaxies, they see something that just shouldn't be happening. They're spinning so fast they ought to fly apart. It's like something invisible is there, acting as gravitational glue, a sort of cosmic ghost holding the whole show together. And that something is what we call dark matter. And we're not talking about some small rounding error here. This stuff makes up about 85% of all the matter in the cosmos. We know it's there. We can literally map out its gravity, but we have absolutely no idea what it is. It doesn't give off light. It doesn't reflect light. It's a true cosmic ghost. For decades, the hunt for dark matter has been all about finding some new, exotic particle that we just haven't discovered yet. Things with names like WIMPs or axions. And that would be huge. It would mean new physics beyond what we know. But there's another candidate, one that doesn't require inventing any new particles. Instead, it just proposes a new kind of black hole. And this is where our story takes a really radical turn. What if dark matter isn't some new ghost particle at all? What if it's a different kind of black hole, one that was forged in the fiery furnace of the Big Bang itself? So the difference here is absolutely fundamental. On one hand, you've got your regular stellar black holes, born from dead stars billions of years after the universe began. And on the other, you have these things, primordial black holes, or PBHs. They weren't born from stars at all. The idea is they formed directly out of super dense pockets of energy in the universe's very first moments. So how would that even work? Well, just picture the newborn universe. It's this incredibly dense, almost perfectly smooth soup of energy. But you've got these tiny quantum fluctuations making little ripples in it. Most of those ripples would just smooth themselves out. But what if, just by pure chance, a ripple was dense enough, so dense that its own gravity became overwhelming? Well, it would collapse in on itself and form a black hole, all within the very first second of time. Now here's the kicker. For this whole idea to work, for PBHs to be the dark matter, they had to be unbelievably rare when they first formed. See, as the universe expands, matter, like a PBH, doesn't thin out as fast as radiation does. So even as they started as a tiny fraction of everything, just 1/1000th of the universe's density, they would have slowly come to dominate the matter budget by today, and it would perfectly match that 85% we see. It's an incredibly elegant solution because you're solving the biggest mystery in cosmology with objects that our current physics already says can exist. Okay, so if this theory is right, the universe should just be filled with these ancient, tiny black holes. Which leads to the obvious challenge. How on earth do you find them? So the hunt has been on for years, and scientists have used all sorts of clever methods to rule out PBHs of different sizes. They can't be too big or we would have seen their gravitational effects by now, and they can't be too small or they would have just evaporated away. But there's this little sweet spot left, a range of masses where they could still be hiding and could still be all of the dark matter. So what kind of mass are we talking about in that window? Well, on the lower end, you have this number, 10 to the 17 grams. It's a huge number, hard to even wrap your head around. So let's try to put that into perspective. This is the truly mind-bending part. I want you to picture a huge asteroid, the size of a mountain, a massive chunk of rock. Now, imagine crushing that entire thing down into a space smaller than a single atom. That is the insane density we are talking about. That's what scientists are looking for. And the ways they hunt for them are just as incredible. Scientists are scanning the skies for the faintest whispers of gamma rays from the smallest ones evaporating away. They're staring at millions of stars at once, just hoping to see one briefly get brighter as a PBH passes in front and acts like a tiny gravitational lens. And with instruments like LIGO, they're listening for the echoes of two of these tiny monsters colliding billions of years ago. It's like they're trying to solve this puzzle from a dozen different angles. So we've gone from black holes we can actually see to a theory about primordial black holes that we can actually test. But the math that describes all of this, well, it contains even stranger possibilities. So now, let's venture out to the very edge of physics, to a concept that might only exist in the equations. I want you to meet the white hole. It's the perfect opposite of a black hole. Where a black hole is the ultimate prison, a white hole is the ultimate source. You can't get in, but things can come flying out. It is literally a black hole with the arrow of time played in reverse. And look, this isn't just some sci-fi writer's fantasy. White holes fall right out of the exact same mathematics of general relativity that predicted black holes a century ago. If you solve Einstein's equations for a perfect eternal black hole, one that has existed forever, the math just tells you that it must have a white hole counterpart in its infinite past. So when you put them side by side, the contrast is it's stark. You can fall into a black hole, but you can never ever leave. You can leave a white hole, but you can never ever return. And maybe most importantly, we know how black holes are made. Stars collapse. But a white hole? For now, it's just a mathematical curiosity, a beautiful ghost in the machine of physics. And really, that's the big problem here. Our universe isn't eternal. Black holes are born from stars, and we think they eventually evaporate. In that realistic picture, there's just no known way a white hole could ever form. They could only exist if they were somehow part of the universe's starting conditions, which makes them way more speculative than even primordial black holes. So, wow, we have taken quite a journey, haven't we? All the way from the concrete and observed to the purely hypothetical and mathematical. Let's just quickly recap where we've been. We started with the monsters we know, the black holes born from dying stars. Then we moved on to the plausible ghosts, the primordial black holes that could actually be the dark matter we've been looking for all this time. We saw the very real hunt that's going on right now to find them. And finally, we touched on the fantasy, the white hole, a beautiful but probably non-existent creature of pure mathematics. You know, this whole story, from the black holes we see to the white holes we can only imagine, it all began as scribbles on a page, solutions to Einstein's equations. We've proven that some of those scribbles describe real things out there in the cosmos. Others, well, they might be real. And it just makes you wonder, doesn't it? What other cosmic secrets are still out there, just waiting for us, hiding in plain sight, inside the math that describes our universe?